Hello everyone, this is Mr. Jackson, and today we're going to pick up with part 2 of Concept 2, where we're going to build off of part 1 for cardiovascular, where we went into a lot of the anatomy and just a tiny bit of physiology related to this system. Remember, this is made up of the heart, the blood, and the blood vessels, and this creates a closed system by which we keep all of the essential oxygen and nutrients going to the tissues that need them, and then we remove the waste products that we don't any longer need, right? So this is a closed system. So for part 2, we want to look a little bit more so into the physiology, the actual way in which we keep things moving along. And the best way to do that is to look at this mechanism that we refer to as a pulse or a heartbeat, because with each heartbeat, that is essentially how we facilitate transport. Okay? It's the heartbeat that keeps this system going, and by extension, all of your systems going. And so we want to make sure that we give that its due credit. Now, when I'm talking about a heartbeat, this is what you can actually hear through a stethoscope. We're going to have, as part of our lab stations in this concept, we're actually going to be able to practice with a stethoscope and a blood pressure cuff as we listen for a heartbeat and we take our blood pressures. So you'll have plenty of opportunity to actually practice with this tool. But what we're actually hearing here, it's associated, this heartbeat is basically what you're hearing are the valves of your heart closing during what we call the cardiac cycle, or the heart cycle, the process by which one heartbeat is performed. So we hear this typically in two sounds, lub and dub, right? So anytime you listen to a heartbeat, you would hear lub dub, lub dub, lub dub, okay? And we want to know what's actually happening now that we have a decent understanding of the anatomy of the heart. Whenever we're talking about the lub, that initial sound, this is going to be made when those atrioventricular valves are closing, okay? So this is basically when the ventricles contract to build up pressure in order to pump the blood out to either the pulmonary or the systemic circuits, right? Remember, the ventricles are those pumping chambers, and so this is going to create quite a large sound. There's a lot of pressure built up here. And so this is where your AV valves, those valves between your atria and your ventricles, close because of the ventricular pressure pushing on them. So this is the point when that ventricular pressure, it's above the pressure of the atria, which basically allows those valves to close and the overall ventricular contraction or systole to begin. So that's the lub. It's the atria slamming, or that AV valve slamming shut between the atrium and the ventricles because the pressure of all that blood in the ventricles has reached a point where it's higher and it can close the doors behind it, and now the ventricles can contract. The dub is made when those semilunar valves, right? That's between either the aortic or pulmonary veins. That's when those valves are closing because the pressure above the ventricles now has risen after the pump, okay? This happens basically whenever those ventricles have done their job and they begin to relax. We call that diastole, okay? And we're going to work with this whenever it comes to blood pressure, because you might hear a blood pressure of 120/80, and that's always referring to systolic over diastolic. And so we want to know what that means and why those measures are valuable. So this is just the first part of that. So lub, AV valves close. Dub, the semilunar valves between the veins and the ventricles are closing. Again, always preventing backflow. So we have this cardiac cycle. This is a step-by-step process that contributes to one complete contraction and relaxation of the atria and the ventricles, all of that cardiac muscle tissue that makes up your heart. Systole is when the heart is contracting, when it's actually doing the pumping. Diastole is when it's relaxing. Now, quick overview of what we're about to go through, okay? I'll drag myself up here. We have these electrical events, or those action potentials. Remember, your heart can generate its own. These are what are going to ultimately stimulate mechanical events, right, due to pressure changes. Now, blood flows through the heart. It's in a controlled system, but it's always controlled by the pressure in those chambers based on whether that pressure is built up in the atria because there's a ton of blood in the atria, or if there's more blood in the ventricles, right? Again, this is a closed system that's basically interacting with those action potentials, those electrical signals, and that becomes a mechanical signal due to the pressure buildup in these chambers. Blood is always going to do what requires the least amount of energy, and so that's going to go from an area of high pressure to an area of low pressure. So it's moving down its pressure gradient all the time. So if it's higher in a ventricle than it is in the veins that would carry it away, that pressure buildup is what ultimately would lead to that pumping contraction. So it's going to go from the area of high pressure to the area of low. Okay, so we want to break down the steps real quick. And again, we are going to practice and practice and practice this time and time again. This is going to be the main skill that we want to have from this concept. But just as a matter of introduction, the cardiac cycle, we are going to begin in what we would call mid to late diastole. Okay, so remember, diastole is referring to relaxation. So at this point, we have relatively low pressure in the heart. Blood is flowing passively through the atria, and those AV valves are opened, okay? So passively, just those AV valves are open because the pressure was higher here in the atria. This allows it to go from high to low, and so we're moving down through those AV valves into the ventricles. A wave of depolarization from those action potentials will then cause the atria to contract. Okay, so remember, it's starting up here at the SA node down to the AV node, and so that wave of depolarization throughout those atria causes a contraction of that muscle tissue. So that's going to basically create an increased pressure where the muscle tissue is going to contract, and then the amount of space available to that same blood is going to get smaller. So same amount of blood, lower space, that is what builds that pressure up and forces more blood through that AV valve down into the ventricles. Okay, so we're forcing it through that open valve. It propels blood into the ventricles, and this is going to result in what we call like a max volume. We have forced so much blood because of that contraction of the atria chambers down into the ventricles. The atria will then relax, so that wave of depolarization has gone. It's passed. And so now that muscle tissue relaxes, but remember, that pressure is going to decrease here. We've got a lot of pressure from all that blood down in the ventricles, and it's that pressure that basically now closes those AV valves shut. Okay, so when those close, there's your lub. Okay, so that's where we are. All of that happened in mid to late diastole right here for the cardiac cycle. Okay, so we got higher pressure in our ventricles now. Now, that wave of action potentials is now down here through that interventricular septum. It's going to create a wave through all of this ventricular muscle tissue. This is going to cause your ventricles to contract. The pressure in your ventricles increases. Those AV valves are slammed shut. And then your semilunar valves, because of all this pressure, in the way they allow it, are going to swing open. All this pressure makes this contraction happen with your ventricles. It's going to push blood out either to the pulmonary or systemic circuits based on what vein it's going through and from which ventricle. So this is that ventricular ejection phase where blood is rushing out of the ventricles into either the aorta to your systemic circuit or the pulmonary trunk to your lungs. And then finally, that wave of depolarization has come and gone. We are going to have early diastole. That muscle tissue is now going to relax. The pressure overall is going to drop, especially because so much of that blood is now gone and the open space is increasing. And this is ultimately going to mean that we have more pressure up here in these pulmonary veins or pulmonary trunk and aorta than in the ventricles. And so now that is what would cause that higher pressure to close those doors behind it, and we would then be able to repeat the process. So the process described above, what we just went through, is for the systemic circuit through the left side of the heart, and then that same process happens going down the right side for the pulmonary circulation. Overall, it's using less pressure, right? Because there's lower pressure required to get blood to the lungs than to the rest of your body. And then despite the differences in pressure, both circuits are ejecting the same amount of blood with each heartbeat. And then finally, guys, we're going to close up this whole concept here. I know this has been 2 very long parts relative to others, but a lot of good information. We regulate this entire process that we've just discussed, even though the heart is perfectly capable of generating its own impulses, contracting on its own at a resting state, let's say. But there are extrinsic controls that would require us to change the overall pace of our cardiac cycle to either increase it or decrease it. And this can be influenced by any sort of change in autonomic nervous system, that automatic system that we don't have to consciously control. So this could be in response to exercise and the requirements that puts on your body, being frightened or scared, feeling anxious. All of these things can increase the overall level of activity. We can have hormones interfering with this process. We can have different ion levels that create more need for those ions and therefore either higher or lower outputs. Age can have an influence. How fast your heart can actually beat is highly affected by age, where it actually will slow down with time. Your max heart rate decreases with time. You can have gender differences. Your overall fitness level and level of health can create a more or less efficient system, meaning that if I'm less healthy, if I'm less trained, then I might have to pump more to get the overall same level of oxygen and nutrients to my tissues compared to somebody who's extremely healthy and their heart can do a lot more with each beat. And then finally, body temperature. Right? Body temperature is another key regulator because body temperature is going to affect whether or not your blood vessels are dilated or constricted. And so that would mean maybe in order to get nutrients to the same place, I need to pump more through these more narrow or wider vessels. So few examples there, guys. Again, these are all physiological concepts that we're going to explore heavily in our lab stations. And we also, naturally, because this is such an important organ, we're going to be able to follow this all up with some dissection for sheep hearts as well. A lot of fun things on the way. That is our lecture in terms of Concept 2. I hope you found it useful, and we will see you at respiratory in the next one. See you.